So we are solution chemistry. And there's so many awesome jokes. So you guys have been opened up this term to a whole new world of jokes and puns in chemistry. So we did that when we had the avocados, like the avocados, when we did moles, puns. I was trying to think if somebody could find, if you found a new, or you could come up with a new solutions. There is a bonus on the worksheet for Wednesday. That's a really fun one. All right, but if you have a really fun solutions related comic that you find, you can email it to me. Tatum's on it already. She's there. I know she's Googling away trying to find. She'll send me like 10 of them, or Brittany will. She does that too. But you should all do that. This is Chem 104. It's driving me crazy. So a solution is a mixture. It's a mix of two things. So you're going to have a mix of, you're always going to have two parts, a solute and a solvent. And the solvent, the solute is being dissolved. It is usually the one that you have less of. So if we're talking about salt water, salt would be the solute, and water would be the solvent. Water is known as the universal solvent. I had a lot of trouble trying to pick what lab to do last week and this week, but I went with the cabbage because that one's so fun. And we'll actually do, those of you who take Chem 105 with me, we'll do the universal solvent as a kitchen chemistry one. Water is not a universal solvent. Water only likes things that are polar, and so the islands of plastic that they have now found in every single ocean show that plastic is non-polar. It doesn't like water. If water is present, though, we say it is a solvent. The solvent is doing the dissolving. So a solution does not have to be water-based. It is the most common type because we are water-based as humans and the earth is, but you can have the air in some ways can be considered a solution because it's a mix of different things. The properties of a solution, I'm going to go through what comes to my mind. There is, I think it's the first or second study set question for Wednesday, I think is a true false, and it has these in it beautifully written. But one of the things with the properties of a solution is it is, the word is not transparent. It is homogeneous. I can't think of the word. And so that means it looks the same. When you look at it, it looks the same everywhere. A chocolate chip cookie is not a solution. When you look at chocolate chip cookie, the chocolate chips are not equally dispersed. And so the reason for this is that the solute is evenly dispersed. It's meandering around and everything is mixed equally about. In a chocolate chip cookie, you guys have all done it. Like sometimes you get the chocolate chip cookie that's like the hallelujah one that has 20 chips in it. And then sometimes you get the one that somehow only got one chip in it. I mean, the store-bought ones are kind of weird because they all are exactly the same, and that's not what happens in the household. But that's probably the biggest piece. And it doesn't settle out. And that is actually something we'll go through here. These are three types of mixtures. So let's just go through that. So these are types of mixtures. And the difference between them, they all have a solute and a solvent, is the size of the solute. In a solution, the solute is itty bitty, teeny weeny. Yellow polka dotted. You know, I put this here, and I always regret that I do because people will memorize these numbers, but it is that they're like smaller than a micron, smaller than a micrometer in size. You cannot see them with our eyes. And so it looks the same throughout. In a colloid, the solute is small. So we can say tiny. You still can't really see it, but they are bigger, and that's going to allow us to do something with this. And in the suspension, the solute is pretty large in size. You can actually see the particles of the solute. An example of a suspension would be mud. So if you look at mud, which we have a lot of it right now around, you can actually see the particles of dirt with your own eyes. Paint is another example. And so something that a suspension does that the other ones don't is it settles over time. So today we didn't have rain, and so most of our mud puddles settled, that the dirt settled to the bottom and you have the water on top. If you paint, like everybody's probably painted, and then 2 years later you're like, oh, we need to touch up this area, and you open your can of paint and you're like, ooh, what happened to it? It's a suspension. The particles, the solute particles, the color particles are so large that over time they just settle out. What that means is you can filter it. And so if you're camping and you're desperate for water, you can use a filter and you will filter out all the big particles. Another example of a suspension is our blood. If you take a sample of blood, don't do this. This is not part of the lab this week. And you take the sample and you let it sit in the test tube. Over time, it will settle. And that is because the red blood cells are heavy enough with the iron, they're dense enough that you will get 2 layers of it. All right, the colloid, the key with that, an example of a colloid is fog, milk, Jello, and actually I think it's our plasma. And so that would be the proteins and stuff. So in the blood, the cells are what settles, but the proteins, the large macromolecules, a colloid does something, and it's the fog, that a colloid disperses light. So if you've ever tried to drive in a really dense fog, it's pretty impossible. It's why our Oregon coast, and actually even here, we get these amazing, you can take beautiful pictures at the Oregon coast or down in the redwoods because there's so much fog, and that is the water vapor in the air is the solute, and the water particles are large enough that when you shine a light at it, it disperses the light and you get these amazing pictures and stuff. But if you're trying to drive in it, it disperses your headlights, and so your headlights are never going straight ahead. They're always going in all different directions. I tried this with the kids class. It didn't work so well, but you make Jello, and if you have a laser, which everybody has lasers now on like their pens and stuff, you can actually try and shine it at Jello, and it won't go through the Jello. It will go off at different angles. And so we tried to cut the Jello to get it to go through a maze, but it's really hard to cut Jello perfectly straight, so it didn't work so well. Example of solution is like salt water, or actually your Coca-Cola. The sugar in Coca-Cola, all the other crap that's in Coca-Cola is not big enough to disperse the light. You can't filter the stuff out. Yeah, it's you cannot filter. It won't separate. The way you can separate it is, I mean, there's tricks we use in lab where you can heat it up and one part will boil off and the other part will be left behind. When we do the study set, the questions, the first page of the study set are very specific because I always know that I'm not going to remember. This is a lot of words, and in the study set, it's written down more elegantly than here. But the key is that a suspension, the particles are much bigger. A true solution, you cannot filter it. It does not separate, does not settle. And this one up here, that it's evenly dispersed throughout everything. All right, this term electrolytes, that was the first Nobel Prize in chemistry in 1901. The term electrolytes, we've all heard it. It's used so much in commercials and stuff. And people be like, oh, I have to get my electrolytes. It just means you have ions in water. And so ions conduct electricity. So in you and me, that's important because that's one of the communication ways throughout our body. Electromagnetism is actually the real way our body communicates. And it's also the way we communicate. It's just that we are not aware of that necessarily. And so we obsess with chemistry and the matter of stuff. All right, these terms are really important: saturated, unsaturated, and supersaturated. Saturated is when you have the maximum solute dissolved. Meaning if you add one more grain, so if we add one more grain, that's not going to work. It does not dissolve. It's maxed out. This is you guys next week. Actually, next week you become super saturated on Thanksgiving, right? We usually eat more than we should. So we go past our saturation point. So saturated means that you're at the max. You can't add any more. You can add and stir and stir and stir. And so you've seen this. People will keep adding sugar to their tea or their coffee. And then at the bottom, when they get done, there's just this layer of sugar down at the bottom. All right, unsaturated, you can guess what that means. It means less than the max. So if you add more, it's going to dissolve. And supersaturated means you have more than the max. You somehow tricked it. The easiest way to do this is with heat. So hot tea will take a lot more solute than cold tea, than iced tea. And then if you let it sit, it will actually stay in there. And so this is also the way people do the crystals. You know, when you buy as little kids, you buy those crystal kits and you heat them up. I think now you just heat them in the microwave and everything looks like it's a solution, and so it's super saturated, and then you let it sit for time and slowly the extra will come out. But it's somehow that it was tricked. To get more than the max. All right. One of the places you see the supersaturated, besides in the kids' rock things, is, and we actually used to do a really fun lab with this where we make alum crystals, is the hot hands that you get and you like crack it and it gets warm. That's actually a supersaturated solution. You'll see the crystals coming out, and as they're coming out, it's giving off heat. It's an exothermic reaction. Or the cold hands. Right now, having cold hands would not be so fun. All right, this is actually one of the gas laws, except it's not with a gas. But as you increase the pressure, you're going to increase the solubility of a gas. so more gas would dissolve. So this is when we're talking about bubbles. This is how they get the bubbles into champagne or into Coca-Cola, is they use pressure and they push it in and then they close it really quick, either with a cork. And this is why when you, with the champagne, you get the cork off, you get that big, because there's so much pressure that was on the inside, and so it just pops off once you release it. Or Coca-Cola, when you open it, people like that, and that's because the inside had a lot of pressure to get all those bubbles in there, and the bubbles will come out. It becomes flat once all the bubbles have come out. The bigger one is temperature, and this is only with a gas. So if you're trying to add more sugar to your tea, pressure isn't going to really affect that. But temperature has variable effects. As you increase temperature, most solids, you increase the solubility of many solids. We'll say many. So the reason I mention that is because the sugar or salt, more sugar and more salt will go into the water if you heat it up. Sugar, it's a crazy amount. It's like almost a whole bag of sugar you can put into a cup of water if the water is warm enough. It's like infinitely soluble. Salt does have, everything has a maximum point, but you actually decrease, with higher temperature, you actually decrease the solubility of gases. And this is an issue, this is probably the biggest issue with global warming that isn't talked about, that the small increase in temperature of water has changed how much oxygen is dissolved in the water. When you're talking about the ocean is huge. So the change in temperature isn't as big as you see, but on streams, small streams, because the water's not super deep, the temperature has changed by several degrees, and a several degree change makes not enough oxygen for fish and animals that live in the water to survive. And so it's one of the issues with the salmon migration, that we want to blame the dams and say, oh, the dam's in the way. The fish can't actually physically get back to their original spawning grounds if there's not enough oxygen in the water. This is also why we chill Coca-Cola in this country. So our sodas, we like cold, because as you decrease the temperature, you increase the solubility of the gas bubbles. So when our soda is cold, it's more bubbly. And in this culture, our country, we like the bubbles. I personally don't. I don't like the cold. I don't drink soda. But when you go to other countries, one, they don't have the refrigeration, but they don't like the bubbliness. And so they drink their sodas warm, and they want a little bubble, but not like we do. And this is also why people chill the champagne, is because the lower temperature means they get more bubbles, so they get a bigger pop. And people, I guess, really like the bubbliness in their drinks. Same with like the seltzer waters and stuff. If it's cold, there's going to be more bubbles. And so if you're somebody who likes the bubbles. All right, solubility, this is a review. We've actually done this. This is the hydrophobic and hydrophilic. How much dissolves? That's experimental. So that was the saturation point. We already talked about that up there. What dissolves? Polar likes polar. And we call that, and so that would be soluble. Insoluble would be polar and non-polar. So that's why our polar bear is there. And so that's hydrophobic, is things that are non-polar. And we actually already talked about that when we did all the IMF stuff with H bonding. So you'll probably see a question again. For those of you who can take Chem 105 and Chem 106, this becomes one of our big things that we talk about, because we are water-based, so things that don't mix with water, and that's the whole big to-do about cholesterol, because cholesterol is hydrophobic, and so if it has nowhere to go, it just clumps and becomes a lump inside of you that blocks your arteries. So that was just some terminology and things that we've actually talked about or you may have known. And when you do the homework, we'll refine some of this stuff. And don't overthink the homework. Just like give it your best go and know that when we go over it, you'll refine it. This is why we're doing this, is osmosis. And if you take biology, or when you take biology, you'll also talk about osmosis. Osmosis is the movement, and this is the key, of solvent. The solute doesn't move. It is the solvent that moves. Now, some of you have taken anatomy and you learn about the sodium potassium pump and then channels open. If a channel is open, if a door is open, sure, anything can go in and out, but this is the movement of a solvent across a membrane. We call it a semi-permeable, meaning it is only permeable to the solvent. Unless there's a door, unless there's an opening for the solute cannot move. And so this membrane means our cell membrane. Our cell membrane is what it's all about. Our cell membrane is the walls around every cell. And so we've been obsessed for the past 50, 60, 70 years with the DNA. They can actually take the DNA out of cells and the cell still survives. It cannot reproduce, but it still survives. But if you take the walls away from your home, if you start getting holes in your wall, you're going to start freaking out because it's going to get cold. It's going to get wet. We actually had that issue this past week because my sunroom had its yearly leak that it gets. So osmosis is all about how our cells can communicate. And it's the movement of the solvent, how things can get in and out of our cells. And again, if there are cell membranes, only solvent, the water can move back and forth. Otherwise, you either have to have an opening, like a door opens, a channel, or you have to have a boat that carries things across. All right. When we do the homework, I think we see more examples with this, and same on the worksheet. So for this, I do pictures. So the prefix iso, does anybody remember? We saw iso before. We saw it twice. We saw it. What?
Is it one?
No, it doesn't mean one, but do you remember when we, it means the same. Yeah, we saw it with isotopes. So same element. And we saw it with the isomers. We did a lot with isomers in the other classes, but it means the same. And tonic means salt. And so this is talking about cells. So here we have our cell, and the cell is very happy. And so I'm just going to make up a number. Whatever number I give you in the question, just go with. So we're going to go with, this is 0.9. Here we go. What's the big M stand for? Somebody must remember what the big M stands for. Say again?
Molar mass?
No, it is not molar mass this time. So this was a question that came up before.
Molarity?
That it is molarity. What is molarity?
Moles per liter?
Yeah, I have no idea who's talking. You guys forgot the rule from like 2 or 3 weeks ago that you're supposed to.
Per liter?
I don't know who's talking.
My camera's on.
I know, my back's to you. Donna, you answered a question? This is like this is like extremely exciting to me. Sorry, I just heard somebody saying they had their camera on. Brittany, I loved your question when we did the homework, so I gave you a bonus already, so you don't have to. And Christy, I gave you another bonus because I shared the cartoon without your thing. So Donna, this is extremely exciting to me because I think this is the first time you've gotten a bonus point during class. The rest you can answer stuff. So the big M is molarity. So solutions are solute in the solution. So moles per liter. But anyway, we saw that way back when on our first celebration. So if it was isotonic, the inside and the outside would be the same. So water is moving, but there's an equal flow of water in and out, and our cell is happy. Hypo, like hypothyroid, low. Hypo means low. We saw that when we did hypochlorite, meant below normal. So hypothermia is below normal temperature. And hyper is going to mean high. So low salt means the outside is low. So our cell, we're going to make a cartoon. He'll be like Mr. Bill. He's like, oh no, he's still 0.9. But now the outside is going to be low. So we'll make it 0.2. We should put our unit. This is so much more fun when I have the huge board to write on. So the water moves, not the solute. The 0.9 and the 0.2, maybe if I make my picture bigger. Here we go. The 0.9 is how much salt is in there. The salt can't move, only the water moves. So the water wants both sides to be the same. So the water moves in. So the water moves to the side with the higher concentration. Molarity is a measurement of concentration. So the water moves where the higher one is. Now again, you have to be careful. If the door is open, then of course the 0.9 will move out because the door is open and so it can spread, but it can't right now because it's a cell membrane. So what happens is our little cell becomes really big, ginormous. He becomes bloated. So all the girls in the class probably know what that term means, bloated, because we've all been there, done that, but he swells up. He doesn't feel swell, he swells up. And we used to do this trick to get DNA out of cells because then you can just poke them and they explode. But then the DNA is there intact, so you haven't damaged, so they swell up. And if they're talking about it with blood cells, they'll often call it hemolysis, that you could lyse the cell, meaning it could burst. So if it's really bad, he could burst. Oh no, that would be terrible. All right. So hypertonic, we have our cell. He's again kind of going, oh no, he's 0.9. And this time the outside is too high. So we'll say it's 2.0. And so this time the water's going to leave him. And it's going to go out. Because it's trying to make both sides the same. So what happens is he shrivels up. So he's shriveled. There is a fancy word for this. And the fancy word is cremate with an N. Not cremate. We're not burning him up. We're not like spreading his ashes around, but we're cremating. This is the idea behind what I'm going to pick on Philip for a second because he's the only boy in here, but maybe some others have done this, but it's always the boys in my class will tell me they did this as a little boy. If you go out, slugs their membrane is a semi-permeable membrane. And if you put salt on them, they shrivel up in front of you, and it's really disgusting. When I first moved to Oregon, that's what my students told me I needed to do because I was alarmed by the slugs, the amount of slugs we have here. Now I'm one with the slugs, and we do fine. And I was horrified. So then my students told me, no, there's better in doing, because I didn't like watching them shrivel up. And plus I ran out of salt because there were so many slugs. They said you just get a can, like an old can, a small, like a tuna fish can, empty, and you put cheap beer in it, like Coors. And so I did that, and I put it out in the garden, and I went out an hour later with little baby Joey in my arms, and it was even more disgusting. So there was a line, there were 5 lines of slugs, like wanting to get into the big beer fest. And the ones that had made it into there, they were all bloated because apparently it was a hypotonic solution, but it attracted like the slugs from all my neighbors' yards. And yeah, now we just accept that there's always a sacrifice of some of the food to the slugs. And I don't have as big an issue as I initially did. But anyway, there you go. You can have fun. You can draw much more elaborate. The problem is, like Christy, now I have like these images of what you're going to draw for me. So there is a term, I didn't make this up, but I've only seen it in one book, and so I think he made it up and it just never caught on, but it was an excellent chemistry book, and it's osmolarity. So we're going to go with it. And what it is, it's not just the concentration. These are supposed to be capital M's. There is another unit that has these little italic M's called molality that we're not going to do in here. So if they are not capital M's for you, just make them molarities. Yeah, I don't remember if I fixed them. So osmolarity is the molarity, you see it there, or the molality times the number of ions that you have. Now, glucose is a molecule. Here we go. How do I know it's a molecule? You don't get an answer now. You gotta like lay down with your table. Anybody? Molecules
I was
are.
right once. I can't be wrong again. I don't want to do it on recording.
Wait, what, Tiffany? Go for it.
I just said because they're together. It's all clumped together. But I didn't want to be wrong again.
What's different about this from my ions?
The parentheses.
We'll let you think about it. If somebody figures it out as we're going, let's go through these. So sodium chloride is NaCl, +1, -1. Calcium chloride, calcium is a +2, so CaCl2. And oh, look, there we have Nick again. Potassium and nitrate.
Is it because there's a metal and a non-metal in the other one?
Yeah, so ions, these are all ions because they're metal, non-metal. A molecule is not ionic. And so that means it is only non-metals. You guys all, oh, you're going, yeah, that was like 2 weeks ago. Feels like a different month. It's because there was a new moon, and so we moved into a new lunar cycle, and you forgot everything. You're all tired. So that feels like 10 years ago at this point. If it is only made up of nonmetals, carbon, hydrogen, oxygen, so there's no ions, so we just keep this number. So it's still, we just say it's 1 osmol. So we put the odds there. We're going over the rainbow with this. All right, for the sodium chloride, we will take the 0.5, and there are 2 ions. There is a sodium and a chlorine. So we're going to multiply by the 2 ions. And 0.5 times 2 is also 1.0, and we go over the rainbow. They need the ions for the molecule. All right. Calcium chloride's the piece here. There are 3 ions. There is a calcium, and then there's 2 chlorines. This is not a diatomic. This is an ion now. And so the subscripts, we count them. So there's 3 pieces in here times the 0.6, and that is 1.8. I think we have a winner. All right, potassium nitrate, Nick. That's why I like those parentheses, even though they're illegal to all my colleagues. NO3 stays together. Nick is taking a nap upside down now. So there are only 2 ions. The polyatomics do not come apart. This is just solubility. They're just floating around aimlessly. So Nick, sorry, he's in the losing one. All right, so we look at these numbers, not these. It's the final number that we look at. So the highest osmotic pressure is going to be the highest osmoles. So that would be our calcium chloride in this example. Osmotic pressure is that movement of osmosis. So the greater these numbers, the more osmosis movement. So it's the solvent movement. It's pulling the solvent into or out of. So the higher the osmoles, more solvent is going to move. This question is actually really important, the electrolytes.
Could you shift your page a little bit?
Yeah. Oh, which way? I know, I moved that down. I can move it up.
Thanks.
That's probably the best way to shift it. So anybody know which ones are electrolytes? Go back. The answer was on this page. We talked about electrolytes. We said they were ions in water because ions mean you have positives and negatives. And for electricity to move, you need positives and negatives moving. So it's positives and negatives moving. So on these examples here, which ones are the electrolytes? Not all of them. All of them but one. Which one? Maybe I should ask this. Which one is not the electrolyte?
The first one.
The first
Yeah,
one, glucose.
the molecule doesn't have ions. So the electrolyte, since I said which one is the sodium chloride, the calcium chloride, and the KNO3. And I have no idea who said that. Who said it first?
Tammy did.
Sammy?
Yep.
Okay. Sorry, there's so many of you with similar names, and then yeah. So it's back to that question about being molecular. The molecules do not conduct electricity. They don't break apart in the water. The rest of you, well, you don't have to answer if you found a fun solutions-based cartoon to email me. All right. Then we do VP, BP, and MP. So VP, anybody remember what that stands for?
Vapor pressure.
That is vapor pressure. So we're looking at vapor pressure. And vapor pressure, was that you, Tiffany? What is vapor pressure?
1 point for me.
Well, actually, you got to answer the full question. What is vapor pressure, though? VP does stand for vapor
The
pressure.
gas escaping.
Yes. So thank you. So it's how much gas escapes. Now, in this case, we're looking at a solution. So it's a solvent escaping. So something I have to tell you before I answer the question. Solvents love their solute. Solvents and solutes, they're in love. They absolutely love each other. The solvent is really, that's why they mix. So on these, which one is going to have the highest vapor pressure? Which one's going to escape the most? And which one will escape the least? Oh, Kaylee made it. Well, the more osmoles, oh, go ahead.
The solvent's going to be escaping the most.
Of which one?
What do you mean?
So the solvent escapes the most. The more osmoles you have, the lower the vapor pressure. So the more solute you have, less escapes because it wants to stay in there. It wants to stay in the solution because it's like, oh, there's more the merrier. Kind of like the opposite of what's going on right now, where we're not allowed to be around, the more the merrier. So this one, the smallest one, would have the highest vapor pressure. There's not as much in there. There's not as much solute. So less solute, higher vapor pressure. You already got a bonus point though, Brittany. All right, BP is, again, how much is the temperature is escapes, right? Oh, sorry, I should have given somebody a chance. Temperature of escape. So I'll give somebody a chance. Which one's going to have the highest boiling point? You really have a 50-50 chance because you can rule out the ones that are in the middle. The monkey's in the middle. Did anybody see my monkey up there? I found my monkey when I went to school the other day. All right.
Is it the calcium chloride?
Yes, that was Shaylee.
Yes.
For some reason, you actually showed up like at the top there on my screen, and nobody else is like, I keep seeing the same people, and you have the little yellow thing around you. I don't know why yours works and nobody else's does. So this one's going to have the highest boiling point because it needs the most jiggles. So as you add osmoles, as you add solute, you you need more jiggles to escape. Speaking of jiggles, reminded me of something I need to tell you. So the lab you have this week has to do with what we're getting to in a moment, acids and bases and pH. I rearranged the schedule because I didn't want you doing pH over the holiday because some of you will get it really fast. We're going to be doing pH on Wednesday, and that study set will be due before the Thanksgiving break. So the lab you're doing for this Saturday, it's due Saturday, is you're going to have to extract cabbage juice. So I posted like a short, like a 20 or 30-minute PowerPoint about it, or you can just read the lab, but you just need a couple leaves of purple cabbage. I think it's purple. Everybody here calls it red cabbage. And then you can make something really delicious with the rest of it. There is actually other options if you can't, red cabbage is in all the stores. And it's actually a bonus if you want to try also to do it with something else, because there's like turnips and all these other things that supposedly, and then you try like, I think it's 10 or 12 different substances from your house. There's a suggestion like of a whole bunch of things you can try. You can definitely go outside of my suggestions, but it does have to be liquid. So a solution that is aqueous. And you're going to be looking at it with cabbage and checking my color scale. So I just want you to be aware of that. So you can get, if you can't find cabbage, there's other suggestions on there of things that you could try. My students did it this summer and they all found cabbage, the red cabbage, no problem. I eat it every day in my salad, so I like it chopped up and raw in my salad. All right, so this one also had our highest osmotic pressure. So we have one more, which is MP. The better way of saying this would actually be freezing point. So FP, so change that. Did it, I may have already changed it.
Yeah, it's FP.
It says FP on yours? Okay. So FP is the freezing point. So it's when the solvent's going to freeze. So again, and this, for a solvent to freeze, we're going to make it into a solid. So going back to our states of matter. Oh, the other thing I wanted to say with the lab, so that's the lab that's due Saturday. There is another lab that's going to post at the end of this week. And it's a 7-day lab. And so you'll have to start it Saturday. And so you'll be doing it over Thanksgiving. And then there's another lab next week. So there'll be 2 labs next week. But the one is, again, one of these things that you do for 7 days. And it should make your Thanksgiving even more pleasant. My other class has been doing it this past week. And so I'm getting to read their comments as they come in. All right. So anybody want to explain to me? So freezing point has to do with the solid. What was special? So what was special about the gas is the jiggles. So we need to get more jiggles so they escape. A liquid flows. But what was special about a solid? Solids and liquids both have attract.
Don't solids stay in the same shape usually? Have like a
Yeah,
solid
so
shape?
Solids have to have, yeah, regular pattern. Regular shape or regular pattern. So they maintain a certain figure. And so if we think about ice, ice is the one that's really special because it forms these hexagons. And what happens when you add a piece, that's my solute, like sodium chloride. This is why we salt the roads in the winter, not here because it actually interferes with the water quality for the salmon and stuff, but in other parts of the country they put salt. They actually use other stuff now that works even better, but it interferes with the pattern. So when you add the solute, it interferes with the pattern. And I'm probably, yeah, with like these new regulations and stuff and like looking around the world, I'm like, I'm gonna have to really get used to how to write with this projector. So as you add more solute, it actually decreases the freezing point. More solute, so this guy, the 1.8 is our lowest freezing point. So the more and more solute you add, you drop the freezing point. The one with the highest freezing point would be the 0.8. It means it dropped the least. So all of them dropped below. If we're talking about water, it's 0. These are all going to have freezing points below 0. The 1.8 is going to drop the most. The 0.8 would drop the least. You know, people add salt to water when they cook. They do it for flavoring, but it does actually increase the boiling point of the water. They use, actually, the thing they found that works really great, this is in Wisconsin, when they make cheese, there's this slimy stuff that's left over that they can't use for anything, and they actually treat the roads with that. I forget what it's called, but they actually found it's like amazing for preventing the roads from freezing, and Wisconsin has lots of problems with roads and stuff. I kind of liked here when we had that big freeze like 5 years ago and everything just shut for 2 weeks, and we just went out like the first few nights, it was just like a winter wonderland. Everybody's out like playing in the snow and stuff, and then everybody got tired of it. All right, let's move on to acids and bases. And so we're gonna work with these more on, yeah, there we go, on Wednesday. On Wednesday, we're gonna do the math. Today, we're gonna walk through the terminology, and so your study set's a lot of words, or circling answers and stuff like that. And then the math. So anybody, what do you know about acids? When you hear acids and bases, what do you think?
pH level.
Yeah, most people think pH. Tiffany, what were you gonna say? Is that the same thing?
Hydrogen. That's all I said.
Oh yeah, that we're going to talk about too. That's actually, so pH, I'll talk about this more on Wednesday because we will be doing pH calculations. It is a lowercase p and a capital H. And that is a pet peeve of all chemistry teachers. And it is pronounced as pH. It is not, I tell you that because I had a sales rep tried to sell me a meter. Actually, no, he was trying to sell me something else. I was busy finishing. Everybody told him he had to talk to me. I was in grad school. Because whatever he was selling, it was something that I would need for my project. And the pH meter happened to be next to me. And he then, for the 10 minutes, because guys can't keep quiet next to a girl working or something, is he talked to me about, oh, who'd you buy the meter from? And I just stopped what I was doing and I enjoyed having a conversation about our meter. So pH, if it is 7, it is neutral. And we'll talk about this again more. That does depend on the temperature. pHs below 7 are acids, and pHs above 7. See, I brought colored pens specifically for this. Oh well. And if it is above 7, it's a base. So the classic example of testing pH was litmus, and litmus turned acids red. Actually, the cabbage, anything that turns pink and red, those are going to be in the acid range. The thing that's really cool with, well, litmus, if it turned blue, it was a base. The thing that's really cool with the cabbage is it turns different. It's blue, green, and yellow. You get a whole bunch of different colors, and different, like the turnips were different colors also. It was pretty cool. Anyway, there's pH is a scale that was actually made up only about 100 years ago. That blew me away because I just thought pH had always been around, but it made the math easier and it made it easier to talk about acids and bases. But the term acid, and actually what Tiffany said is most people, when they think of acid, you think of the hydrogen, and it's not hydrogen, it's actually hydrogen ion. And why this is special and why acids get this dangerous sign is going all the way back to our second lesson, that we used to put numbers with hydrogen. So maybe somebody who hasn't gotten a point yet, what did those numbers mean? Does anybody remember that 1 and the 1?
The protons and the entire mass thing.
Yeah, the protons and the, starts with an N?
Atomic number.
Neutrons.
Oh, wait.
Neutrons. It was your protons and neutrons. And the lower one is your atomic number, which is just your protons.
Mm-hmm.
So we'll give it to Kaylee.
Sweet. Thanks.
I love that everybody's names rhyme in some way in our class. We could write like this beautiful like poem, Dr. Seuss book about this class. There's Kaylee and Haley and Shaylee and everything. All right. So anyway, it has 1 proton, and 99.9% of hydrogen is a mass of 1, which means it's 1 proton and 0 neutrons. And when it gets a plus charge, it loses its electron. So it's also not an electron either. It's only a proton. So a hydrogen ion is a proton. And this is why they burn, because protons, remember, were tucked way deep inside in the nucleus. They had their big castle around them, the electrons. It was empty space. But now it lost that castle and it wants a new castle. And so it burns. It eats away at metal. It corrodes. It's extremely useful. It was in the alchemical periodic table. They thought it was an element, but it was used for everything. Common ones in our house: Well, it's right there. Lemons, right? So citrus, vinegar. So some of the things, a lot of the stuff that you end up testing ends up testing out acidic. And that's actually part of why I made that PowerPoint, the video that's up there, is I usually spend a lot of time on this, but we're not going to tonight. And so I found it was easier with the pictures and stuff. But one of the things that is really cool is the word acid actually means sour. So it is Greek for sour, and so that's where the term comes from. And so anything that you taste has a sour taste is acidic. So does anybody know what a base tastes like? And there's a hint over here. The bases tend to be are cleaning things other than vinegar. So soaps tend to be, so does anybody know what soap tastes like? So this is the unfortunate part. Kaylee, I don't think you should know what soap tastes like, but I usually get to ask this live where I can actually see all of you, and usually about half the students will raise their hand because they actually had the situation where their mom put soap in their mouth because they said a very bad word once they were a kid. And so, Kaylee, hopefully that didn't happen to you. Anyway, you should all watch it because there's a picture of Kaylee in there from when
Brittany
she was.
said bitter.
Yeah, so they're also bitter. So soap, I don't know if soap has a bitter taste. I've never tasted soap.
It tastes terrible.
Anyway, anything that has a bitter taste, so coffee and chocolate, they are actually basic. Another term for base is alkali. So the 1As and 2As, remember, were alkali metals and alkali earth metals. And that is because when you mix them with water, they give us hydroxides. And so bases we usually think of as hydroxide. Now, the comment for you with, we'll get to that when we get to the things. There are actually other definitions of acids and bases. This was the original definition was hydrogen hydroxide. And then as we got to know more, we realized that was a really limited definition. It's a definition most people know. The definition that chemists usually go with is that acids are proton donors and bases are proton acceptors. So again, a proton is a hydrogen ion. And when we do the reactions on the next page, we'll see that. So in the video, I talk about that a little bit. The first guy, Arrhenius, he talked about him as hydrogen hydroxide. And then Bronsted and Laurie came up with this, which is, and again, a proton is that hydrogen ion. So still the same definition here. All right, one of the things, and we'll see this also as we go through the practice, organic chemistry is the chemistry of carbon hydrogen based, and organic acids are going to have carbons and hydrogens, and then they're always going to end with CO2H. So that's the acid. It is, so the number of, this is an X and a Y, the number of carbons and hydrogens doesn't matter. It is this piece here, and this is what it would look like as a Lewis structure. And so I mention this because an issue that a lot of students have is as soon as they see an OH, they think, oh, that's a base. It's not actually like that. This is if you have a metal plus the OH. This is not a metal, this is a molecule. That's what we were talking about earlier. So what happens is oxygen is so super greedy that the oxygen is pulled, the double oxygen, it has to be that you have the two oxygens there. That double oxygen pulls the electrons and it makes it that this hydrogen just is easy to donate. So it's that double oxygen. So the double oxygen makes it easy that this is the hydrogen that donates. Carbons attached to hydrogens, this is non-polar. So that's not going to be donated. It is that pooling of the electrons that allows it to be an acid. So this is a very, very polar bond. It's not actually a hydrogen ion, it's that the water, because it's such a pull of the electrons, that water can pull that hydrogen off. Organic bases, so this was the acid. If we're going to do a base, carbon, hydrogens, and you're going to see nitrogen. And there might be hydrogens with it, there might not be. That doesn't matter. The reason nitrogen, let's put hydrogens with it just for the heck of it. This part, I'll put a question mark because those hydrogens don't matter. It's the nitrogen. Nitrogen's everything. These nitrogens, if you remember back to when we did Lewis structures, those nitrogens always had a lone pair of electrons. And this lone pair of electrons is that hydrogen ion is attracted to it. So if we go with the definition that a base is something that accepts a hydrogen, lone pair of electron attracts the hydrogen. So nitrogen's lone electron pair attracts the proton. And that is why it is a base. So our mantra, when you see nitrogen, it's a base. And that's why that original definition is limited. All right, the next terms are pretty straightforward. Protic means proton. And mono means one. So there's only one proton. Example would be HCl. Has only one proton. Poly means many. So H3PO4 would be an example of a poly. It has 3 hydrogens that it can donate. It donates one at a time. This is mono. These hydrogens do not come off. Hydrogens on carbons are nonpolar. They're neutral. So this part of it is neutral. You should write that in purple. All right. And again, this is the purpose of the study set. The study set is to help refine all of this. All right, the next term is, again, proton, amphi. So the example I always give is about amphibians. So amphibians were named amphibians because they live in the water and they live on the land. So they can be either or. People who are ambidextrous can write with their right hand, they can write with their left hand. And so this can be an acid or a base. The second word that I wrote after it, amphoteric, that's just another term that you might see in some places. I use the word amphiprotic. So examples would be bicarbonate, HCO3 negative. So it can donate this hydrogen. But that negative means that it can attract a hydrogen. So which is it going to be? And it's going to be whatever it needs to be in the situation. So if it's in a situation where it needs to donate a hydrogen, it will donate. If it's in a situation where it needs to attract a hydrogen, it will attract. So it's a switch hitter. It can act, maybe we should write those there. It can act as either. The classic example of an amphiprotic compound is H2O. H2O can either donate a hydrogen, So if it donates a hydrogen, it will become hydroxide. So it lost the hydrogen. And it can accept the hydrogen. So OH is hydroxide. We saw that term before, and we're going to see it a lot in the next week. If it accepts a hydrogen, it becomes H3O positive. So the charge does change because it's gaining or losing a proton. So if you lose a proton, if it donate means it loses. So you have to be careful. This is not Leo. That's not an electron. It'd be losing proton. So Lu. So it's not. It's becomes hydroxide. Here it's accepting or gaining a hydrogen, and this is called hydronium. Because hydrogen ion is a proton, it actually never exists. It will either be as hydroxide or hydronium. Because as a proton, that's just not possible because of the nature of what a proton would be, the subatomic particle. So in biology classes and all your other places, if you work at a pool, anything you talk about is hydrogen and hydroxide. It is truly hydronium and hydroxide. And so in here, we're going to see that term come up. All right. 2 more pieces. So again, today's the wordy day. Conjugate acid, you're going to see me just abbreviate this as Ca. And the conjugate base, you're going to see me write it as Cb. So let's do it with the bicarbonate. So if bicarbonate is a base, then its conjugate acid would be H2CO3. So it gains a hydrogen to become its partner. So these are always, a base becomes a conjugate acid. The opposite would be if HCO3 is acting as an acid. And again, when we do the next page and as you do your homework, these are just, this is a lot of words and the words will start making sense more with practice. In this case, it donates. It's not gonna work. Acid donates the hydrogen. And in this case, if it's a base, it gains a hydrogen or attracts a hydrogen, whichever way you like. So in this case, if it's going to donate, it's going to become CO3 with a -2. So it's going to lose this hydrogen. It's going to get donated off. So this is its conjugate base. And again, when we go, it has to donate it to somebody else. So there's going to be reactions here. There's going to be something else happening. Like in this case, it could be if it's an acid is going to give it, like HCl is going to give it a hydrogen. Here, a base is going to take away the hydrogen. So before we do the practice, we just have to get through these words. So as I'm using them with the practice on the next page. And the last one is, and this is, again, I made that video with the PowerPoint that's for your lab. And so the lab also should hopefully help with all of this. And it's what Wednesday's lecture is, the math with all of this, is strong versus weak acid. Strong acids, I abbreviate as SA, and they completely dissociate. This is something I mentioned before when I originally talked about acids, when we did nomenclature. The acids do not actually ionize. They are not ions. They're very polarized bonds, and so the water pulls them apart. So they completely, another way of thinking of it is they donate their hydrogens, all of them. there are only some strong acids, and we're going to make a list so we have it. And that is, these are my strong acids: HCl, HBr, HI. There originally were only 6. These lists do vary from places online, so we're going to go with this list for our purposes. H2SO4 and HClO4. Notice, especially here, we get to the ones that have lots of oxygens, because the oxygens are really pooling, which makes this a very polarized bond. And halogens really pool. But notice HF is not on there. So these are the strongs. You put them in water, they completely dissociate. That means it's a one-way reaction. And again, I keep saying when we get to the next page, these terms will make sense. That was reaction. So a weak acid. Wa is the, so this is for weak. They partially dissociate. And partially means 5% or less. So it's not like, oh, only 90%. These guys, really, it's usually like less than 1%. They only partially dissociate. They only donate some hydrogens. They don't want to come apart. So like this guy up here, only, so remember you're gonna have Avogadro's number of this molecule. So 6.022 times 10 to the 23, only some of them are gonna give up the hydrogen, but not all of them. If you have any of these, they completely will come apart, and we'll see that. And so this is all the other acids, which is good news. So lemons are weak acids. Vinegar is a weak acid. They are still an acid. They can still do what they need to do. When we work with a strong acid in lab, that's why when that balloon, when I did that demo, the balloon, it kind of scared me because I used a strong acid and I'd never done it before. I wanted to see what happened, and it just blew up so fast. I thought it was going to blow up in my face and I was going to have sulfuric acid all over the place. But it didn't. It just reacted really fast and then it was done. All right. The key here is what ends up being our very last topic in 2 weeks, which is you're going to start seeing, it's where I have to come clean from all those reactions we wrote. We made everything as one arrow. The worksheet you're turning in tonight, your study set, everything was a one-way reaction. That's actually a lie. Very few things are one way. Most reactions go in both directions. And so it's a two-way reaction. It's kind of like how we drive, right? Most roads are 2 ways, 2 directions. And so it goes back and forth. And so this is called equilibrium or equanimity. And normally we study equilibrium first. That would put acids and bases as our very last subject, and that would be just too much for all of us to end with like pH calculations. So we'll end with equilibrium, which is a really nice balanced way to end everything. All right, we're going to see these terms on the next page, and then in the homework you get to put it all together. And remember with the study set, we'll go over it. I'm just looking that you tried it, you answered all the questions. And then as we go over it on Wednesday, you will want a colored pen so you can add to it. You'll be wanting to take notes as I go through it and adding comments to it. And the worksheet's actually not that bad, but And then again, there's a video goes with the lab for this week. And then there'll be, yeah. All right, so acid-base reactions. So this is a question Brittany had asked me. They are called, let's just go through it. So what we're going to do is we're going to go through these steps. I am going to give you your acid and base. It doesn't mean it's acid plus base. It could be the base plus the acid. So we want to identify which is the acid, which is the base. And I'm just going to write A and B. A for acid, B for base. All right. So H2SO4, I'm going to make that list up here. Remember the SA? Here we go. One more chance for a bonus. What does SA mean?
Strong acid.
Yes, it is strong acid. You already got a bonus, Brittany. She's like,
I'm just saying, nobody else was saying it. I was just saying it.
I know.
I'm just hearing crickets here.
You're fine. That's actually was the biggest thing for me when I was first teaching, was to learn how to, I like have to take like 3 breaths, like really slow, because a lot of people, they have to do that thing where they get the courage up, or they have to wake up, or maybe they're not there. My other class, only 2 people ever answer, and I'm pretty sure that several of people just like turn on their black screens and then go back to sleep. Oh, Nick, HNO3. All right, some books also put HClO3. Don't worry about it. I'm not gonna, but these guys are the strong acids. What they mean when we see one, you want to write SA, not just A, but SA. Because we're only going to do 1 arrow.
Mine is different than your first one.
Oh, what's your first one?
HCl plus NH3.
All right, let's do that. Thank you. I rewrote them, and then we're having computer and printer communication issues suddenly started happening today. So I just pulled up the old ones that I had a blank copy of. So if any of my other ones are off, please tell me. So HCl is also a strong acid. And it means that we're going to have 1 arrow. Nitrogen. Something else I did say back here. You see a nitrogen, you're thinking base. You see nitrogens, you write base. That's a big take-home thing. When we do in Chem 105, we finally get to nitrogens at the end of the term. With proteins, proteins are cool because amino acids have an acid and a nitrogen, so they're both an acid and a base. What's the word? Brittany's like, I'm taking 3 breaths. I'm taking 3 breaths. You can answer Brittany if you want.
Is it
Amphiprotic. Huh?
Is it conjugate base?
Oh, that's what we're going to do. No, it was that they are amphiprotic. They can act as an acid or a base. But what we're going to do here, this is how I do it for teaching. The students who do it this way always get it right. And on the first one, you might want to. The acid donates 1 hydrogen. So I circle the hydrogen and I do a little loop. And it's going to give that hydrogen to the base. So you're absolutely right, Philip. What's going to happen is the HCl now becomes a Cl negative. It lost its hydrogen. The hardest thing for students is the charge, because you're losing the positive, the Cl becomes negative, and this is called the conjugate base. It can't be a conjugate acid that doesn't have a hydrogen. The acid becomes the conjugate base. The nitrogen now picked up that hydrogen, and it's now got a plus because it has the extra hydrogen, and it is going to be called conjugate acid. So the acid becomes a conjugate base, the base becomes a conjugate acid, 1 hydrogen. These are what type of reaction that we just went through in your study set and worksheet. And oh, Brittany wants to answer. Does anybody else want to answer before she does? She's going to.
Single exchange.
Yep. That's what I
No,
think.
it is an exchange.
Double?
It's a double because they both were compounds to start with. It's harder to see because you're right. What you're seeing is that 1 hydrogen. Yeah, maybe this
Double.
wasn't the best example. Yeah, that wasn't the greatest example. So don't just erase. Can we erase? Go back. All right, on B, is my B example the same as yours, Tiffany? CH3CO2H and H2O. And the next one, C6H5NH2 plus H2O.
Yeah.
Okay. Okay. And then they might change.
The only one that's different on yours is the E.
E?
Yeah, E is H2SO4, and then the ending is the same.
And this one's the same?
Yeah, everything else is
So,
from what I can
see, if you see the ending CO2H, acid. Some students write WA for weak acid, or you can just write acid. It's kind of up to you. It's not as strong. It means you're going to put 2 arrows. That means the water is the base. On the next one, if you see nitrogen, you are not writing acid. If you see nitrogen, you're writing, this is my base. That means this time, water is the acid. Water is a switch hitter. Water will be whatever it needs to be. So if you have plus water, water will be whatever is left over. So acid, water's the base, base, water's the acid. It is a double arrow for both of these. So let's do it. On this one, this hydrogen moves over. So CH3, ignore my 6. CO2 negative. It lost the hydrogen, becomes negative. When you do the study set, be like, I was having trouble with the plus and negative. Get the idea at least of them switching and say, I'll fill in the plus and negatives as she goes through it. Kind of allow yourself, you don't have to be perfect. You're going to get your 5 on the study set, do the best you can, and then realize it's supposed to be a learning experience. This is going to be called the conjugate base. The acid becomes the conjugate base. All right, and then plus the H2O picked up a hydrogen and it becomes the
conjugate acid.
acid. Anybody remember what H3O was? Hydronium. All right. Next one. The water is the acid. So the hydrogen moves from the water to the other one. So the other one is C6H5. Carbon does not pick up hydrogens. Carbons are nonpolar. They don't want more hydrogens. It is the nitrogen that was the base. So the nitrogen picks up another hydrogen. So NH3 positive. So again, when you pick up the hydrogen, hydrogens are positive, becomes NH3 positive. This is the conjugate what? What's the base? It is
Acid.
the conjugate acid. So the base becomes the conjugate acid. And then plus, if water lost the hydrogen, what is it?
Hydroxide.
It is hydroxide. That's our conjugate base.
Good one, good one, good one.
All right, on the next one, they both have hydrogens. Only one of them gets to be the acid. Which one's the acid?
H2PO4.
It is not the H2PO4 because the H2PO4, I did this as a trick question.
Oh, it's the H because up here the strong acid is HNO3, but this
No,
one
it
just
says this is HNO2, but the H2PO4 has a negative. That negative means it has a place for the hydrogen. So this guy is amphiprotic. Again, this has lots of information, and it's going to take time, not necessarily between now and Wednesday, but just make notes. This guy was amphiprotic. He could have been either. It had hydrogens, but that negative, this one has no choice. So Brittany, you're on the right track, but it is only an acid. It's a weak acid, which means 2 arrows. It's an equilibrium. It's going both ways. So this guy gets to be the base in this case, our amphiprotic one. So this hydrogen on the acid joins the other hydrogen, and we get H3PO4. It no longer has a negative. This is our conjugate acid. The HNO2 lost its hydrogen. It becomes NO2 negative. It's the conjugate base. All right. So before I do the last one, I want to talk about this chart down here because the D was written for that chart. KAs, these are equilibrium constants. And the A means for acid dissociation. As you increase the value of the Ka, more dissociates. So more hydrogen donated. No. So what do you notice about all these exponents?
negative.
They're all negative. These are all really small numbers. So on this list, which one has the highest Ka? The top or the bottom? The top. So this is our highest Ka. Yeah, and it is like 8:05, so sorry. We can go for about 5 more minutes. So the higher the Ka, the more hydrogen donated. We call that stronger acid. It's not a strong acid. Strong acids do not have an equilibrium. They're one way. They completely went. They're stronger acids. So the reason I mention that, if you have a one-way reaction, you're done, you do your one-way reaction. If, this is what all of these words, if there's 2 arrows, so we only have to do this if there's 2 arrows, we predict the direction. So we predict the favored direction. And it is always from the stronger to weaker. The stronger always wins, meaning it pushes. The stronger pushes more. And so you only do this if there's 2 arrows. So if we look, so the strong acids always win. They're one way. If you see hydronium or hydroxide, this is like step 1. Step 2, if you see hydronium or hydroxide, they push. They're like above this chart too. So for these B and C, the reaction favors the reverse direction. So they push better. And then step 3 is you look at Kas. You only have to do that if you get something like D, which we have here. You look at the acid, HNO2, and it was Ka of 4.5 times 10 to the negative 4. And you look at the H3PO4, it's actually higher on the chart. So I don't know why I'm writing this, but this one is stronger. It's not strong, it's stronger, meaning it's pushing more. So it's going to push that way. It would mean if we drew our arrows, we'd have a little arrow going forward and a bigger arrow going back. So even though it's a two-way street, it's kind of like rush hour. Everybody is going one way, right? During rush hour, everybody's leaving. So this thing's saying, nope, I want to go back. This is like, I want to go this way. Nope, going back. So it always goes from the stronger is pushing more.
Okay.
Let's do last one. Last one's nice. Last one's not, because we see a strong acid. So one arrow. That means this has to be my base. Only one hydrogen. So only one hydrogen moves. So HSO4 becomes a negative. It's my conjugate base. All right, we have to make room here. So this is why I said they're like a type of double. I was jumping the gun there. The sodium and the hydrogen switch places. So you can do one of two things. You can move, the sodium's going to move over here. That will cancel out my plus and minus. And now we have room for the hydrogen. There is another trick where you just cross out the sodium. Sodium doesn't matter. Sodium doesn't affect pH at all. So if you prefer, it's like a 50-50 mix. Some students will do, okay, I'll just switch it. It's like our exchange reactions. Or you can just cross the sodium out, and then you would have your negative, and that would have had a negative. This is my conjugate acid. I'm going to do one last thing, and then you're free to go. And that is, oh, actually, we'll talk about this. This is unstable. This was the question I've been waiting for a week, because when I made that balloon blow up, it was actually, I think, this reaction. And I was really hungry and wanted to be done. And so I didn't explain it, but how did the balloon blow up? And it has to do with there's CO2 is trapped in here. Do you guys see the H2CO3? If you pull out the CO2, it's going to be the gas, and that's how I blew up the balloon. And what you're left with is two hydrogens and an oxygen. So this guy actually always breaks apart into H2O and CO2. It's a trick our body uses. It's part of respiration. It's how respiration influences the pH of our body. When people get hiccups, it is when their pH is off, and it's a way of getting rid of a huge amount of CO2 in one. And so when people have hiccups where they can't control them, it's usually an indication that your pH is off of your blood, and it's usually an indication your kidneys are not functioning correctly, because that's how we usually regulate it. We'll talk about that more on Wednesday. But unless there's a question, I'm going to stop recording, and then I will hang out if people have questions on their worksheet. All right. Stop.
Hey,
No.
Sherpa,